Hello students, this is Dr. Ujjwal UP, Assistant Professor, Department of Humanities and Science, KGRD College of Engineering. Today we will discuss one of the topics of quantum mechanics, that is important topic of quantum mechanics, that is Davision and Germer experiment. So this is the first experiment. This is the experiment having profound implications in quantum mechanics and development of quantum mechanics based on the concept of wave nature of matter, fast moving electrons behaves like a waves. So this they proved the wave nature of electron. This is the first experimental evidence of matter wave, and it was given by two American physicists, Davision and Germer, in 1927. And we will see the experimental setup in the next slide. Apparatus actually in their experiment arrangement, uh, they observed the electron diffraction and interference patterns also. They accelerated the electrons from hot tungsten plate. First, this apparatus consists of electron gun, where electrons are produced, and when the filament of electron gun is heated to dull red electrons are emitted due to thermionic emission. It is the emission of electron because of thermal energy. So now electrons are accelerated in the electric field of known potential difference. These electrons are collimated by suitable slits by applying high tension battery to obtain the fine beam of electrons, because they would scatter otherwise, and these electrons are then directed to fall on the target single crystal of nickel, that is a target. So they studied the diffracted or scattered electrons from the nickel target. This is the experimental arrangement of Davision and Germer, which was conducted in 1927. So here we can see the hot tungsten filament is there. This F is the hot tungsten filament. This filament was maintained a steady potential difference between F and this plate by low tension battery. Electrons emerged through a fine opening, and this electron were made fall normally on the surface of a nickel crystal N. These were made to enter through these two plates called A, and this is connected to the high tension battery, because in order to make get the fine beam of electrons, these were applied across the electron beam high tension battery, and these electrons beams are finally made to fall on nickel crystal or the nickel target. And using the Faraday cylinder, these after hitting the nickel target, these electrons would scatter in all the direction. So they would collect the electrons from in certain angle from say 20 to 90 degree. This is the graduated scale. So this on upon this scale there is a movable collector which collects the electron coming in certain angle with respect to the incident electron. This is incident direction of electrons, and this is say a particular angle of scattering theta. So from angle 20 to 90, they set up the graduated scale. Among in these angular range scattering, electrons can be collected. So actually it's scattered in all the direction, but they studied for this 20 to 90 degree scattering angle, and there is a collector. This collector can be moved across the graduated scale, because this with this movement we can get the angle of scattering, that is the angle between incident and scattered electrons. So using the Faraday cylinder, SC, this is the Faraday cylinder, and the intensity of scattered electron is measured in all the directions. So the collector C is that this collector C, this can be, as we discussed, this can be capable of rotating about the axis, and this intensity of scattered beam, because number of electron gives amount of current, because this is ultimately connected to the galvanometer. So more the number of electron at particular angle, so at that particular angle more current will be obtained, that is we can get from the deflection shown in the galvanometer. So the collector has two walls, that is insulated from each other, and the retarding potential is maintained between them. So only fast moving electrons are coming through the slits. So now there is a relation between this particular, that amount of current observed in the galvanometer. Amount of current is directly proportional to number of electron coming at this particular angle. So this number would change, vary, as this movable collector, when we move across this various angle, number of electron would vary, and this in turn gives the different color current intensity in the galvanometer. So they found that there is particular relationship between the current intensity obtained in the galvanometer with respect to this high tension voltage which you are applying for making electron to move, making electron move fast through a single beam. Thus galvanometer connected shows the deflection. So this is the basic, and this is entire setup is kept into the vacuum chamber, so that electron would not scatter because of presence of some impurities, dust and air turbulence. So that's why it is made vacuum. So electron cannot uh, deviate from the straight line path. So this is the basic experimental setup of Davision and Germer. Here we will see one small conceptual question. In this experiment, please tell students, can you tell somebody that how electron is proved to be the wave nature in this experiment? Because we know electron is a particle in nature, but in this experiment they proved electron as a wave nature. So please think about this, how electron they proved as a wave. Okay, students, we will discuss this now, how electron is proved as a wave in this particular experiment. So this is the diagram which shows the nickel crystal structure, because they used the nickel as a target in this experiment. So this is the incident angle. So they found that this is the planes of nickel crystal. These are interplanar distance. Interplanar distance for nickel from X-ray diffraction, it is found to be around 0.91 angstrom 10 power minus 10. So these are the different planes which are parallel to each other. So this is how the arrangement of atoms in the nickel crystal. So when the incident electrons from the nickel tungsten, it falls on nickel crystal, it scatters in various direction. That particular, at this particular angle 50, this 50 degree, they found that very high number of electrons scatter in this particular angle 50 with respect to the incident electron direction. So this is the 65 because total 180 degree this line complete is 180 degree, so this side will be obviously 65. So in between this is the 50 degree, this is the angle of scattering. So at this particular angle they found that most number of electrons are collected in the collector, that is we have seen the Faraday's collector in the last slide. So most of the electrons collected at this particular angle 50 degree, and that too for this particular voltage 54 volt. That particular voltage is high tension, which we have discussed already. High tension battery is connected to the this potential to create the potential difference, so that electron can be made a fine beam. So this high tension battery voltage at 54 voltage and at this theta of 50 degree, they found highest number of electrons being collected, and consequently current intensity measured in the galvanometer was highest at these two particular values. These values are very important from your exam point of view, because you have to accurately remember these values and represent this one. 54 voltage of high tension battery and 50 degree angle, most number of electrons were collected by the collector and more amount of current was produced. So they uh, compared this with the interference pattern by Young's double slit experiment. Interference pattern, there was a central bright maxima, and on either side it was a secondary maxima, tertiary maxima, like that. So in between two bright fringes there is a dark fringe. So dark fringe in the sense there is no light. So wherever the places where we get bright fringe, it is constructive, a result of constructive interference, and other places it is a destructive interference. Same bright dark fringe type of pattern was observed in the galvanometer, but here there was not light. Here it is a current intensity. One at particular angle there was a bright, there is a high intensity of current, and very neighboring place it was low intensity, again high, again low, again. So it was very much correlated with interference pattern observed by Young in his double slit experiment. Young, the scientist physicist who conducted the double slit experiment. So by inference they, because interference pattern always exhibited by wave nature, because unlike for example even diffraction can be explained by particle nature also, that is particle can bend, or I mean particle can scatter, but interference can be explained only on the basis of wave nature of light. So here the similar interference pattern in case of current intensity, with respect to current intensity, was observed. So they concluded that this is similar to the interference. So electron would be behaving as a wave, because it is also showing the current intensity bright, and low intensity, high intensity, low intensity. So these alternative high and low intensities were observed in galvanometer. So they concluded that this would be because of electron behaving as a wave. So and they calculated the value with this experiment. They used the Bragg's law. Bragg's law, we all know, 2d sin theta equal to n lambda. So d is we know this is interplanar distance 0.91 angstrom, and that is for nickel crystal, and 2 into d into sin theta. Theta here they took it as 65, because this is the 65 degree angle, because this side would be 65 and it is 50. So if you subtract this from 180, you will get 65. So with this experimentally they calculated the wavelength of electron, because here electrons are being studied for scattering with the nickel crystal. So when you substitute this all this value into this sin theta equal to n lambda, n is the order of diffraction or order of interference, here in this case intensity, because for bright intensity or the largest intensity of current we take n equal to 1. So if you substitute all this value, they got after substitution they got lambda of wavelength of electron as 1.6 angstrom. So 1.6 angstrom wavelength of electron for this particular voltage, 54 voltage. So again they cross verified this result with the help of de Broglie wavelength, the concept of matter wave given by de Broglie in 1924. So he gave the formula for wavelength lambda equal to h by m. So h is the Planck's constant and mass is the mass of electron and m and v is the velocity. And when they substituted it in the de Broglie equation, surprisingly they got wavelength equal to 1.6 angstrom, which is very much similar to the experimentally observed wavelength, that is 1.6 angstrom. So as the two values are in good agreement, this experiment confirms the de Broglie concept of matter waves also, and with this they concluded that electron would behave as a wave. So with this we'll end this concept here, this unit, this particular Davision and Germer experiment. So next class we will see the Schrodinger time independent equation. Before that, the Heisenberg uncertainty principle, which has direct consequence of this dual nature of matter. Thank you.